Okay, welcome back. Today we're going to do the lab for Chapter 9, that is the chapter on support vector machines. And as usual, we have some imports and we have some new imports. So today we're talking about support vector machines, in particular support vector classifiers. So that's what this SVC stands for. There are other estimators, support vector regression, and other things that we're not going to talk about. So that's the main estimator that we'll use from scikit-learn today. The other thing we're going to do is compare classifiers using an ROC curve. And so there's a nice way to plot an ROC curve for a given estimator that we'll use from scikit-learn. And finally, we wrote a little helper function to sort of display some of the boundaries of the support vector classifiers that we'll use that will help us visualize what these things, how these things work. Okay, so we're going to use our support vector classifier, and let's just make a toy little data set here. So I'm not going to dwell on the code we used to make it. For us, we're going to look at the points today. So we're going to start off with a case where the two classes are not very well separated, or they're not actually separable in this case, and fit a classifier to that to see what kind of support points we get and how the support changes a little bit as we change the cost parameter. That's the main parameter in support vector classifier. Okay, so here's how we fit a support vector classifier. We have to give it a cost parameter, and if you remember in the class we discussed how that cost parameter plays. The higher the cost, the more support vectors we have, and the wider the margin is. There's also this argument here, kernel, and we'll see we're going to use a linear kernel here. That means that the boundaries are going to be determined by linear functions. There are other kernels. One of the most commonly used kernel, which we'll see later, is the radial basis function kernel, also a Gaussian kernel. So these are the two main arguments you have to choose when fitting a support vector classifier. Okay, so again, it's a scikit-learn estimator, so we fit it the same way, and we can predict the same way. So here's the plot, the function. We've made this function plot SVM that takes a feature matrix and an outcome and a fitted classifier and plots the decision boundaries as well as the support points. So in this SVM linear, there's information about what points are used as the support points, and we've labeled those with a plus here.
I see. Change colors on us. The reds have become greens now?
Yes, yeah. That's a bit unfortunate. Right. That is likely oh, well, I didn't replot them. It plotted them itself.
Yeah.
Yes.
That's all right.
Yes. Okay, so what we see here is the decision boundary. It is linear for this linear classifier, and these points here, these are points within the margin, and these are the points that are sort of on the wrong side of the margin. They are marked here with a plus. So these here should be green, and these here should be blue. Okay, and there are about 25 points there. I'm not exactly sure. So we're going to change the cost parameter, 0.1. And actually, I think I misspoke before. There is a parameter. So yes, to my defense, there are a few different. Let me say, how did I misspeak before, Trevor? Please go. No, I see it now. It is the cost. So the cost, if there's lower cost and being on the other side of the margin, you'll allow more points on the other side. And that's. Yes.
I was hoping you could just let that one slip by.
Okay.
But anyway, you picked up on.
Yes, well, I mean.
Yeah. So the smaller the cost, the more support points you get.
Yes.
So you pay less of a price for being on the wrong side of the margin.
Yes. And I would, slight difference. There's some people parameterize cost inversely. So. Yeah. And then I would have been okay in that case. But it matters actually how it's parameterized. And so with this cost, the smaller one means there's smaller cost being on the wrong side, so it's easier. Okay, and what we're meant to see here is that there are more support points. There are about the same number of support points, but there are some regions like this region here that have come in. And if you could look at the margin, let's see, this point here must not be in the other plot. Let's take a look. That's the farthest one. See, that point is not across the margin when I use 10.
So in a sense, the smaller the cost, the more points, the support points you got. And that means the solution's somehow more regularized because you're using more of the training data to determine the orientation of the margin, of the decision boundary.
That's right. Like yes, the slope of this line here is determined by somehow averaging the points of these two different, the points on each side.
Exactly.
Yeah. So if you only have a few, then it will be less robust. Okay, so since it's a linear classifier, you can actually find the direction of the decision boundary, and that of course would be not this direction here, but it would be this direction here, sort of that you can use to determine the classifier. Okay, well, we have this tuning parameter C. We had used two values before, 0.1 and 10. Why don't we see if we can find a good one automatically? Well, this is what one of the nice things about scikit-learn, of course, is that if you have an estimator, you can pick a cross-validation method like five-fold cross-validation or a train test split, and then you can use this grid search CV to try and tune that parameter. So the parameters that we're going to search over are given by the second argument, and here this is a dictionary with the argument C being the possible values that we'll look at C from 0.01 to 100, fitting the grid search.
Yeah, and by the way, we saw the cross-validation in action in the labs for chapter 6 as well.
That's right. That's where we encountered this grid search CV. And so it's picked the best parameters and the cost being 1. So, and like in chapter 6, the best estimator is stored as grid.best_estimator_. So we can use that to predict new methods going forward. Okay, so let's take a look at how this choice was made. As we saw in chapter 6, the grid computes the test score as a function of the different parameters. And we can see here's the mean test score, in this case accuracy. And actually, although it picked this value 0.1 here, that's the index corresponding to 0.1, there are actually 4 different cost parameters that gave us the same classification code. So it's not necessarily a very very clear-cut choice that 0.1 that 1 is the best. But
so since small c's correspond to more regularization, it's choosing the most regularized solution that gives the same
among the same
errors.
Yeah. Okay, and if we want to evaluate, this estimator, again, the grid.best_estimator is the one that was tuned by grid search CV. We can generate new data from the same distribution and compute a confusion matrix. So here we're just going to generate some new x's and y's using the same data generating mechanism as above, and we'll compute the predictions using our best estimator and compare them to our actual labels. And here our classifier got about 70% accurate, which is pretty close to the 74% that and then we only used 20 points. We could have used more. It might have gotten even closer to 74%. Okay. So if we, instead of taking the best estimator, we choose one that was not a parameter that was not chosen to be best, like something very small. So this is quite regularized, right? Now I'm getting the index wrong again. Here it's 60% on this data set. So, it did seem to make a reasonable choice at choosing 0.1. At least 1 seems better than 0.001. Okay, let's also, we're going to look at an example where we can linearly separate the data. So here we've just moved the means of the red and the blue points a little bit further apart. And if we fit the support vector machine, we should see that it should be separable. And here we put a very large cost here. So this if the cost is not, I wonder if any cost, if for a very high cost, it should pick the separable solution.
Right.
But for low cost, actually, off the top of my head, I'm not sure if it would pick the separable solution.
No, it wouldn't.
Yeah.
It would still allow
Yeah.
more support points. Yeah.
Okay. And here we can see that this is a case where there's a very few support points compared to the 20 or so we had before. We had 3. So if we sort of change this class a little bit or this class a little bit, these points here that are the support points are likely to move, and hence the plane, as we discussed before, formed by these support points might also be quite variable.
Yeah.
Yeah. And of course, there are many separating hyperplanes here, so we'd expect this to vary a lot as we change training and test data.
As statisticians, when we look at this plot, we see that the decision boundary is determined here by just 3 data points. And so that makes you suspect it's not that robust, right? Because these are data points are on the boundaries of each of their classes. And, so they, as Jonathan said, change the data a little bit, and that can change the orientation of the decision boundary dramatically.
Yeah, and there's also, this is one separating hyperplane, but there are many here, right?
Yes.
Yes.
Exactly.
Yeah.
Yeah.
Okay. Okay. So I'm just going to move on to the next topic. And this is, we saw above the linear support vector classifier. So that's used as linear decision boundaries. One of the main uses of support vector classifiers is for nonlinear boundaries. And the way it does that is changing this kernel argument. Earlier we used kernel as linear. Other popular choices are polynomial or radial basis function kernel. So the radial basis function kernel, that's a Gaussian. So it looks something, like this. And then, so under the hood, what's going to happen is there will be each point in the 2 classes will have a potential little radial basis function attached to it. And the weights we saw for the linear decision boundary will be attached to the points to multiplying those bumps we saw before. So in this case, the decision boundary is going to be where some linear combination of bumps, like this bump and that bump, where that's 0. Yeah. So it's going to be some kind of possibly complicated shape. Okay, so we're going to make a slightly more complex data set here, and by hiding sort of one class between one red class in between two blue classes. So let's just take a look at what our data looks like here.
Oh, yeah.
So this is one where we wouldn't expect a linear decision boundary could do very well, right? Because there's blue, any way we cut through the red, there's going to be blue on either side of it. So using this radial basis function, if abstractly, we could put a big bump here, a big bump here with positive weights, and then maybe a bump down here with negative weights, and that might separate the classes pretty well. It's not exactly doing 1 or 2 bumps like that, but it's doing some linear combination of bumps to try and make a good boundary in a nonlinear space.
That's a weird data set, isn't it?
Yes. Yeah.
I wonder why we chose that one.
Well, I think to make it more complicated.
Because the next picture looks really good.
Yes. Okay. So we're going to do a training and test split to evaluate a bit later, and we're going to fit our SVM on the training data. So here is the part where we actually fit the support vector machine. We give it this kernel argument as radial basis function. We still have this cost, and then there's this gamma parameter. And this gamma parameter sort of determines the size of the bumps. Not necessarily the height, but really the width. So I've just made it one. So as you change gamma, you'll get different sizes like that. And you should check the documentation whether the radial basis function looks like e to the minus gamma x squared over 2. That's going to disappear. Whether gamma is above or e to the minus x squared over 2 gamma down there. And that will make a difference as how you vary gamma, whether it makes a bigger one or a smaller one. Okay. So let's see what's happened.
Ah, look at that.
Oh, wow, that did really well.
Yeah.
It must always do really well, right?
No, it doesn't always do really well.
Oh, that's too bad.
In this case.
Yes. So we did pick a data set for which, some nonlinear method like the radial basis function will produce a nice plot. Obviously, any particular method is not going to work well in every case, but we're trying to illustrate how you can use the radial basis function to make a nonlinear boundary. And here, it did relatively well. And again, these points here indicate the support vectors. So the decision boundary is a linear combination of those bumps, and it has a weight for each of these points here. Adding the bumps with those weights makes a function on the plane, and this decision boundary is really the zero set of that function. So when it's positive, let's say we'll classify as blue, which was originally red, and when it's negative, we'll classify as blue.
Yeah. The support points aren't as intuitive in this picture as it was in the linear one.
No, it's not clear why we have these far points. And that's because there's a linear separation in a higher dimensional space, and we're only seeing some sort of the two-dimensional picture here. Yeah. Okay. So let's see. Again, we can change this cost parameter. So if we increase the cost parameter, that should be, we'd expect to see fewer support points, as we did in the linear case, and actually with a quite high value here. We have gotten rid of a lot of these support points around here. And
you're going to get more wiggly solutions now, because what it's trying to do is not misclassify any of the training data.
Mm-hmm.
So it's going to make its decision boundary wrap around to
is an example
make sure
here.
there's no mistakes.
There's a little tiny island.
Yeah.
If we compare that to the previous one, it's considerably smoother. It doesn't have any little islands.
So overfitting in a case like this.
Yes. Yeah. So let's see what the grid search thinks is the best parameter. So now we're going to look at an example. We'll use the grid search CV again, but our radial basis function support vector machine has two parameters, a cost and a gamma, and we're going to use the grid search CV function as we have in other examples to find the best parameters. Now, one difference in this example is that we have two parameters, so the argument we give for the grid of values is a dictionary with two entries, one for the cost and one for gamma. But other than that, it's an estimator that we fit, and it still returns the best parameters. But now there are two parameters in the dictionary because we had two grids, a grid of costs and a grid of gammas to search over. So this is practical for small grids and simple estimators. If you have many parameters, of course, this is going to be a lot of estimators to fit, and that might take a while. Okay, so it tells us cost 1 and gamma 0.5 is the best estimator. And we're going to evaluate the accuracy of this best estimator on our test data and take a look at the decision boundary. Okay, so we produce our predictions on the test data, as we always do. We've stored the best estimator as best underscore SVM, and we make a confusion matrix as we saw in chapter 4, and it does quite well. It has about 88% accuracy here. Okay, let's take a look at the decision boundary. It got a little push down in this file here. But if we look at this one, it looks pretty smooth, similar to the one we saw, our first set of parameters, and perhaps has a few fewer support vectors on the outskirts, but it definitely looks smoother than the very highly flexible one, with a very high cost.
Looks really good.